Okay, so it's my pleasure to introduce Światosław Gal from Wrocław, and he's going to talk about semi-bounded cohomology. So
on the contrary, it's my pleasure to be it. And yeah, what I'm going to talk are things old and new. And the reason I would like to speak about old things is that we wrote it twice, and it wasn't right. And there is no reason to write it right again. So therefore, I'd like to speak about it. When I say we, I mean myself, of course, and Jarek Kantra. Okay, so about 15 years ago, Jarek invited me to reprove a theorem of Polterowicz, and let me start with writing assumptions of the theorem. So it says that whenever X sigma is a symplectically hyperbolic compact manifold, and I shall stop with the theorem at this place because I think there are things I should explain. So how deep should I go with explanations? Should I say what are symplectic manifolds? I'm very great. Thank you. So symplectic manifold is a manifold and sigma is a true form on X with two conditions. One is that it's closed. And the second condition is that it's not non-degenerate. And this non-degenerate condition can be stated in few equivalent ways. One is that one is to say that X is even dimensional, and if you take the top power of sigma, you will get nowhere vanishing form. The other way is to say that for every non-zero vector, tangent vector, you can choose some other vector such that sigma on this pair does not vanish. The other one is to say that sigma gives a map from vector fields on X to one forms on X, and this map is an isomorphism. And actually, I think this is the best way to say it, because in particular, it tells you that whenever you have a function, you compute the derivative of this function, then you build a vector field. Okay? So the inverse of this sigma makes vector fields so-called Hamiltonian vector fields. On X. And the motivation comes from classical mechanics. So in classical mechanics, you consider a cotangent bundle to X, and there is a canonical one form which is easy to describe. You just take a vector which is tangent to this thing, you squash it onto the base, you get the vector which is tangent to X, and then you pair it with the point where you are. Okay, so it's called the Liouville form, and the magic is that if you compute the derivative of this guy, you get something, of course, closed and non-degenerate. And then if you start with some function which you morally think is the difference of kinetic and potential energy, you are getting your vector field, and you study this dynamics. That's what classical mechanics is about. That's one source of symplectic manifolds. The second word are so-called Kähler manifolds. Those are complex manifold with metric such that complex structure is parallel with respect to Levi-Civita connection. And then if you take this metric, you plug complex structure at one place, you are getting something which is skew symmetric, and the fact that J is parallel with respect to Levi-Civita tells you that the derivative of this guy is zero, and it's non-degenerate because it was non-degenerate Riemannian metric. Okay, so those are two words. Here you have necessarily open manifold. Here you have closed manifolds. Of course, there are trivial examples. Those are surfaces with volume form, right, where everything is satisfied on the nose. So in my case, I start with a compact manifold, but immediately I go to the universal cover. And what I need, first thing what I need is that if I take the universal cover and I look at the pullback of sigma, it is derivative of something. Okay, I have this primitive. This condition is called symplectically a spherical manifold, and it's easy to check. So the only obstruction for being a derivative of something is that already in X I have some bad sphere on which the sigma evaluates to non-zero. Okay, so this is the same as integrals of sigma over spheres are zero for every embedding of a sphere in my X. But also I need something more, and this thing more is hyperbolicity, which reads that I can find such lambda that with respect to some or any, its equivalent, metric from X pulled back to the universal cover, this lambda is a bounded section of the cotangent band. So there are two examples to see when it happens and when it does not happen. Let's go to this case that I have a surface with hyperbolic surface with genus at least two. Then universal cover is hyperbolic space, and if I uniformize it, I can think that this P star of sigma is nothing but dx wedge dy over y square when x and y are standard coordinates in the upper half plane. Okay, and I see that this guy is derivative of x dx, sorry, over y. And this thing, if you check with the metric, is something which has length equal to 1. Okay, so this is a bounded primitive. It shows that homogeneous surfaces are in fact symplectically hyperbolic. Okay. And there is another example, that's the surface of genus 1. Okay, and in this case, the universal cover is just R2. And again, if you uniformize it, you can think that the pullback of sigma is just dx times dy, which is which is a derivative of something, say dx times dy. And of course, this thing is not bounded, but also you cannot find a bounded primitive, which can be checked in the following way. Assume that I have a big disk in this R2. So by Stokes formula, the integral of lambda over the boundary is the same as integral of d lambda over the whole disk. So if I put absolute value, I'm getting this inequality. But here, this thing is just area of the disk, which is some constant known to few times r square, and this thing is a bound on the primitive times the length of the disk, which is also some constant known to few times the radius. So this cannot be true. Okay, it's called isoperimetric inequality. So this is not symplectic not symplectic hyperbolic. You cannot find bounded primitive. This one is. So what is known about what is the class of symplectically hyperbolic manifolds? Those are heterogeneous surfaces. Those are products. Those are hyperbolic, not hyperbolic, Hermitian symmetric spaces. So which are the Lie group over maximal compact from one side and some lattice on the other side, provided there is a complex structure, and there is a number of those. And also there are some techniques, symplectical techniques to make new symplectically aspherical manifolds. And also Jarek proved that whenever you have hyperbolic symplectically aspherical manifold with Gromov hyperbolic fundamental group, then you can do something to get a symplectically hyperbolic formal on it. Okay, so yeah, it's not empty class, I would say. So what did we do? Or what first I will say what did we do, and then what does it prove about those manifolds? What was the original Polterovich statement? So we define, what should I say about cocycles of groups? Is cohomology of groups something I should discuss or not? So let's treat it as a black box, and maybe I will say something more in the future. So we define the function okay, sorry. I told you that there is a procedure of making from functions vector fields and study flows of those vector fields. Actually, these functions which I start from here, I take a function, its derivative, make a vector field, and study the flow. This function, it could change in time. It's not a problem. So all those diffeomorphisms which could be obtained this way, they are called Hamiltonian diffeomorphisms. Okay, there is a little discrepancy between Hamiltonian symplectomorphism or diffeomorphism and those diffeomorphisms which preserve sigma. Those groups differ a little, but not that much. Actually, I should say that because here everything is connected, right? I study flows, so I'm staying in the same connected component. So there is a little discrepancy between Hamiltonian diffeomorphisms and those diffeomorphisms preserving sigma, which are in connected component of identity. There is a difference, but let's not concentrate on this. Okay. So even on all the symplectic, all the diffeomorphisms preserving sigma, I can define a map. So where are I don't know if I'm doing something wrong. So just yeah. So this makes sense, okay? And it's very easy to check that it actually satisfies the cocycle identity, which is G of GH minus G of FGH plus G of FGH minus G of FG equals to 0. That's an easy computation. Okay. That's easy to write. A little bit more technical is to show that if I look at G, and that's a place I have to pause and try to think which one is non-trivial. No. Yeah, probably this is non-trivial. If I fix G, I'm getting the function of one variable. And I claim that this thing is bounded. There is some bound. So this thing is bounded by something depending only on G. Okay? So we called this thing at this point, which was something like 2011, we called this semi-bounded cocycle. We were studying this cocycle, proving that on some subgroups of this group, it's non-trivial. On subgroups, it's actually a differential. Many things, but one of observation which was non-trivial was that this satisfies such a bound. Okay. So then we defined some function on a group which which was a wrong definition. The right definition should be that for any G, we define the supremum of all those values, GH over H1, minus infimum over all H2 of GH2, which we call oscillation of this G. Okay? The span between the biggest and the lowest. It's still. Okay. Now I have this G. What should I write? Yeah, I should write this. I should write this cocycle identity twice. Okay. For H1 and for H2. Same thing with H2 here. And subtract. If I subtract, this thing goes away. If I now choose H1 and H2, which approximate this guy, well, so this difference is close to this supremum minus infimum. And move this to the other side, I'm getting on this side almost the term, the length of F times G. And here I'm getting two terms for G and for F, almost for F and this element GH1, GH2, right? But both of them are smaller than terms for G and for F. Okay? So I'm getting on the north inequality that length of FG, almost the length of FG, is bigger than length, is smaller than some of the lengths of those two guys. And going with this almost to zero, I'm getting the inequality which I need, that the length of FG is smaller than length of F plus length of G. Okay? This terms cancels. This terms goes to this side. I choose H1 and H2. Good for this guy. And there is one more thing to explain. I'm interested in this group. There I was speaking about this group symplectomorphism of Semibounded color. So I claim that there is an embedding. And to claim so every group on the bottom, when you try to lift it to the top, it could happen that it does not lift, that you get some extension with some subgroup of the Tate transformation. So in order to know that you can choose an isotopy on the bottom and start it from identity at the top, and the result does not depend on this isotopy. You need to know that whenever you have a loop in X, loop in this group, and you look at the evaluation map to X, okay, there is a map which is okay, that's exactly what I'm saying. Consider a loop in this group and look the trace it on a point in a space. You are getting again a loop because it ends an identity, and you ask yourself, is this loop trivial or non-trivial? So in this case, it's non-trivial. That's the result of Lalonde, and that's why I need this thing and not identity component of this torus. That's not true, as you can see on the torus, right? The torus can rotate along one of the circles, and then this evaluation map is just one of the regions. So for every element of this group, viewed as a subgroup of this group, there are 2 points. There are X and Y. Even in X or say leads of those points, such that this integral of X Y of G star lambda minus lambda is not trivial. Okay. That's yes. Okay. So in our case, we start with G because we would like to, our aim is to show that this thing is non-zero. In a moment, I will show you. Okay. So we start from G. We have those 2 points, X and Y. And we know it's easy to construct for any 2 points a Hamiltonian map which moves one point to the other. It doesn't need to write it. Nice topic, which is called the finger rule, because you just trace the curve with your Hamiltonian. It's not but so that h of x equals to x equals to y. Okay, and then if you compute this integral, you are done. Our G is exactly the thing from Matthias Strauss. Moreover, you can prove that this thing grows linear. So actually, I want to show it. Yeah, you okay. Let me skip this proof. It's true. It's boring. You just use cocycle identity and you show that actually this guy is equal to n times g, with one caveat. So the caveat is that I define this g with help of some x. Then I told you that Matthias Schwarz gives me an x. So this is a statement which is true for particular x. And I don't want it. I just want to have one cocycle and the statement. So what I need to check is what is the dependence when I change nx. And the thing is that those norms, they are bounded distance. If I change x, the difference is finite. So this linear growth is true up to finite constants. So in particular, what I truly should write is that if I divide this by n, then there exists some constant such that this thing is bigger than this constant. Okay, and this is the statement which is independent on which manifestation of g I took. Okay? I have a whole family of g's indexed by x and primitive lambda. The dependence on primitive lambda is not obvious to me. Okay. I'm not sure what I should say about lambda. So I was considering this example with universal cover being the upper half plane. Okay, and I have this one primitive, but there is the whole group of isometries which acts. And the point is that if I move this primitive by isometry, the difference gives me bounded change in G. Okay, but I feel that there are many other primitives for which this is not in bounded distance. So I'm not sure what I should say for lambda. So everything depends right now heavily on lambda. The dependence on x is controlled. I get a family of metrics bounded distance in each other, but which grow linearly on every level. So what Polterowicz proved, he also used Matthias Schwarz lemma, but then other complicated arguments, and I think our job is our approach is much simpler in this second. So he considered a group, finitely generated group, and then mapped into this Hamiltonian diffeomorphism of x, and finally generated by, say, set x as, say, heighthful embedding. And the claim was that for every G, the word length of G with respect to this generating set for every G there exists positive epsilon such that every element grows linear. Okay. So what we built, we actually built a metric of Ham-X with this property for the whole Ham-X. And then we can pull back the metric to gamma, and the word metric is the biggest metric. So we produce some metric with this property. So the biggest metric also has this. The question one should ask, and we don't know how to answer, is what are continuous properties of those metrics? Or maybe could you somehow replace those metrics by something else of bounded distance with good continuity properties on how. There are various topologies, so I'm not sure what is the right answer. Here, for the purpose of this theorem, you think of Ham as discrete group, uncountable, strange, discrete. Okay.
So we don't know if this compatible with any of these topologies.
No. I can say. I was once asked this question, and I thought for a while. I remember. Okay, then control the time. Okay. So up to saying it right, this is what we knew 10 years ago. And also around this time, a little earlier, Jarek wrote another paper with a few statements, and one of the statements was that whenever you have symplectically hyperbolic manifold, then its fundamental group is not amenable. And he used arguments in a spirit of this isoparametric network. And what I understood immediately was that this semi-boundedness property does not hold only for this group. I should not say that this is what we actually holds not on the whole this group, but on this group and so on. Okay. So it holds not only on this subgroup of this group, but also on pi1, which is group of Dexter transformation, which also is here. It's easy to check. Okay. So if you consider the map, okay, so there are two statements. So can I free my hand?
Yes.
Okay.
You said it also so pi1 is just pi1 contains pi1 of x, but does it contain this Hamiltonian, or is it a big?
No. It's contained in the symplectic.
But
it preserves sigma.
I see. It's not related to Hamiltonian.
No, it's not related to this group. It's another. As I told you, our second paper, third paper, and second paper was about different subgroups here. When this sigma is trivial, non-trivial. So in particular, so I should say that this cocycle, that's a credit I have to give. This cocycle was initially studied by three guys: Losik, Ismagilov, and Michor. Okay. We wrote our paper, which had exactly the same title as their paper a few years later, and it was pointed to us by Kochik that we are overlapping something already existing, but it was not exactly the same, so that's good. And one observation is that whenever you have this sigma, and now I should say that this cocycle identity it exactly describes second cohomology of the classification space of, in this case, I'm thinking about fundamental subgroup, fundamental group as a subgroup over there, right? There is a classification map which gives me a map into second cohomology of X, and this sigma goes to the, not sigma, sorry, this G goes to, at least its class, goes to the class of sigma in here. Okay? That's standard easy observation. Okay. But since this guy has this boundedness property, then I can use another standard method. I can so assume that this pi1 is amenable. So if pi1 of x was amenable, I can take a mean of this function with respect to my invariant mean on the group. And this guy would be a primitive of G. Okay? If it was amenable, hey, mean of G would be a primitive of G, which shows that this guy cannot be non-trivial. And this one is non-trivial because its top power is a volume form non-trivial guy in here. Okay. This shows that fundamental group cannot be. Yeah. Well, then we started to scratch our head. What is this word of not quite bounded cocycles, but with this type of this type of control. Okay. So although you could make a general statement, so you consider n cocycles, and if you haven't seen those, you can solve a problem. You can solve a puzzle. What is the right formula for cocycle identity? How you generalize this word? How you memorize it? I would like to stick to just this word. The word of two cocycles with this one bounded, or maybe n cocycles with this one bounded property. Okay? It's easy to see that this condition agrees with taking differentials. So if you start with something one bounded, you are getting something one bounded. So you have a chain complex of one bounded stuff, and you have this H, what we call H n1. Okay, and you have a comparison map to Hn, and what I said on this blackboard tells you that if gamma, this is the group on which I'm considering my cocycles, if gamma is amenable, then this map is 0. Okay. So how do you understand this and why is it important? So although we were considering many times group extension, somehow it completely slipped our mind to ask ourselves what happens to group extension if you use such a cocycle to build a group extension. Turns out this quite old and quite known construction which doesn't come from Gersten. That in this case, or actually that's a characterization, at least for finitely generated groups, when group extension is quasi-isometric to the product. Okay, that's exactly what you need from cocycle, which defines group extension, that the word metric on extension would be quasi-isometric to the proof. Okay? So it's not so bad, but then for a while there was this question hanging in the air. Are they other examples than just bounded cocycles with this property? Okay, so of course I gave you example on a group of Ham, and I have no idea if it's bounded or not. If you can find a bounded representative, this one for sure is not. But people, and also on pi 1 you have example. But if you think a little, you will see that it actually comes from a bounded thing, bounded cocycle. So for a while, people were looking for such an example, and we were informed of their activity only after we wrote the paper which is on archive in its not final form at the moment. And those were Alessandro Sisto and Francesco Minizia and someone else, sorry, Roberto Frigerio. Yeah, that's probably the people who recently wrote a few papers about them. They actually consider not this group per se, but its image in here. Okay, and they show in two papers. First paper was finally finally generated group, then even finally presented group, when the image of the map from those one bounded two cohomologies in here is strictly bigger than the map from bounded two cohomologies in here. Okay, so that's a completely unrelated research which ask the same questions. Okay, so we are maybe if we knew what they did, we would not write anything. But since we wrote, so the idea was how you describe this guy in more pedestrian terms. So there is a map which takes such a one bounded cocycle. I will skip gamma and maps it to usual cocycle, n-1 cocycle with values in L infinity of gamma. How you just treat the first slot in this cocycle as your variable. So this thing it does not commute with the differential, but if you compute what is if you compute what is d lambda plus lambda d, you jiggle a little with notation, you will see that you are getting so this thing decreases degree by 1. This guy increases degree by 1. So we are getting a map from here to Cn of functions, and you are just making a map into constant functions. Okay, every cocycle with constant coefficients gives you a constant function. Okay. So here you have a map J into C n-1 with values in n infinity modulo constants. Okay, and now if you consider the how do you call it if you stick two maps together? Composition. Yeah. Sorry. If you consider this composition, that's a chain map. It commutes with the differential, right? Because the constants are cubed. Okay. So I claim that this map is an isomorphism after you go to the cohomology. Okay, and this Hn1 is the same as Hn-1 with those coefficients. Okay. There is also one more metric. Because the second question one should ask is what is the so here I said something about the image, right? At least amenable groups. The question would be what is the kernel? Okay. If you study bounded cohomologies, you know that the kernel of the comparison map for bounded cohomologies are quasimorphisms. The kernel of the map from H2 bounded into H2 are differentials of quasimorphisms. And quasimorphism is a map such that Q of GH minus Q of G minus Q of H is uniform bound. Okay? Here is quasimorphism. If there exists a C with this property. So if you consider those one bounded guys, then you get differentials of some other guys. That's differentials because they are trivial in here, okay? And those guys are exactly given by this condition. Okay, so if you have such a condition, this thing is irrelevant. You can accommodate this into C. So that's the condition you are interested in. So those are those functions which translated from left, okay, are in bounded distance. What are those functions? Function on group, if you translate it from the left, it's in bounded distance from itself. So we call these functions abstractly Lipschitz. Why? Because so if we define the length of the Q is supremum of over G, this left translate of Q minus Q, okay? This gives me a norm on a group. Again, easy exercise. And this function is just one Lipschitz with respect to this norm. On the other hand, if I have a function which is also easy. So differentials of, I will drop abstractly, Lipschitz functions. Yeah, but I said it, like I said, there is some length functions such that the function is Lipschitz with respect to this length function. So in particular, your group was finitely generated. From the beginning, there is this biggest Lipschitz function in suitable category biggest, which is length function with respect to the generating the word norm. Okay, so if your group is finally generated, Lipschitz means Lipschitz with respect to the word length. Okay, so after we understood this, we thought, okay, there is simply nothing to prove that's too big, right? If you consider quasimorphisms, you hardly believe that there are any, other than homomorphism, and homomorphisms are killed by differentiation. So quasimorphisms, they shouldn't exist at all morally. And if they are, it's a result. Lipschitz functions, there are everywhere. Okay. So that stopped us for a long time before we wrote this paper. So my co-author, he had a dream, a very crazy dream, to use this to show that Thompson group is not amenable, right? To check that some cohomology elements for Thompson group are one-bounded. They could not have survived this map if the group was amenable. But this is not the case. He managed to show that they are actually not even one-bounded. And it was also a little bit too late, because there was a recent paper of Lara Law who proved that bounded cohomology of Thompson group is trivial. Okay? It's I think it's related to this question. Yeah, I think my time is over, so I can drop here. Yeah.
Does the word metric on gamma with respect to S induce any metric structure in the space of cochains with coefficients in L infinity of gamma?
Does a word metric on a group gamma
Yes.
induces some
Kind of a metric structure, maybe not the genuine metric, on the space of cochains with coefficients in L infinity of gamma?
Yeah. So here you would like to have some other module?
Yes.
No, this map is pretty much onto. I mean, you just relax one. You take it. Yeah, that's an isomorphism on the level of chains. You just treat one of the slots as argument. So here on the level of chains, you have equality. Yeah. Yeah. Here somehow you're losing a little, which doesn't matter for when you pass to homologies. This lambda is an isomorphism.
Another question?
So you said that amenable groups cannot arise as pi1 of x. these.
Symplectic hyperbolic guys, yes.
But is it no, is there a class of groups that is known to arise, that is guaranteed?
So as I told you, any okay, people say class, I'm not entirely sure. What Jarek proved is the following thing. Assume that you are a fundamental group of a symplectic manifold, and the group is hyperbolic according to Gromov, then you have a symplectic hyperbolic symplectic form on the thing. If I'm not mistaken, maybe not the same form started. Maybe it's not about this form, right? Okay, you can probably change the form, the symplectic form on the manifold, and then it's okay. If I remember the logic of his proof. But if you ask me what Gromov hyperbolic groups are fundamental groups of symplectic manifolds, I must say I don't know. For sure, you know that there is this. Is there? I think that there is this necessity of you know having non-trivial H2 for the group. But there are for sure there are some constructions, right? Maybe not purely group theoretical, but you can do some chirurgy on symplectic manifolds and change your fundamental group. And there is this sport of proving which groups could be fundamental groups of Kähler manifolds, which group could be fundamental group of such and such manifold. So this Polterovich theorem is kind of abstraction for a group to be. Oh, okay. No, it's a difference. So the answer, the true answer is not a general one, but there are constructions.
Okay, no. So what's fine?
Thank you.
Running out of you.